I'm Seema and welcome to part 3 of the chapter, The Solid State. In this video, I'm going to tell you about crystal lattices and unit cells. Imagine when you have to make a building, what do you need? You need bricks, and these bricks are arranged in a certain way. And when you arrange these bricks in a certain way and expand that arrangement in 3 dimensions, you get a building or a structure that you are building. Like the Lego blocks that you had when you played with as kids, you join them in certain patterns and you get different structures. In the same way, when you have crystalline substances, in the crystalline substances, these bricks or the minimum structure in chemistry is known as a unit cell. And when you expand this unit cell in 3 dimensions, you get a structure, a pattern. That pattern is known as the crystal lattice. And the crystal lattice, when it follows a certain pattern, that particular substance exists in the form of a crystal, which has a definite specific shape, specific faces, and that is why you have diamonds which have a specific cut. They have specific surfaces. So that is the reason why crystalline substances have got definite structures, just as your arrangement of bricks in a certain way will make a building of one type, and if you had arranged the bricks in a different way, you would get a building of a different kind. Now, you could imagine the lattice to be somewhat like the Rubik's Cube. These are little cubes, and the little cubes have been all joined together. When you join these little cubes, each of these little cubes is a unit cell. And the unit cell, when you expand it in 2 dimensions, you get this one surface with 9 unit cells. And then when you expand it in 3 dimensions, you get this giant cube, a bigger cube. And the cube is nothing but the expansion of the same structure in all directions. Which gives, since the cube is a very symmetrical structure, what you get as a result of it is also a symmetrical cube. On the other hand, if the cube was, the unit cell, the cube was not a cube, it was, let us say, a cuboid, like this shoebox. If it was cuboidal, then the shape of if you had these as bricks, then the arrangement, how would you do the arrangement? This way, and how are you arranging the next brick? This way, or are you fixing it this way? So how you arrange the unit cells, in what pattern do you repeat it? That would make the crystal lattice. And that is why, based on the kind of unit cell that you have, you would get different kinds of crystal lattices, which would then cause different structures of different kinds of crystals. So that is the reason why different crystals have different shapes, they look different, their colors are different. Of course, that is due to their chemical properties, but the structures are different because of the difference in the pattern and the difference in the original unit, the brick itself. The brick could be a cube, the brick could be a cuboid, the brick could be a cuboid with tilted edges. Instead of all being 90 degrees, it could be slightly tilted. So how the unit cell is, there are different types of unit cells, and then these unit cells, how are they arranged in 3 dimensions to create different types of lattices. Now, the scientist who described these lattices, there are 14 types of lattices, and they are known as the Bravais lattices. And Bravais was the scientist after whom these lattices have been named. And there are 14 types of Bravais lattices which are created on the basis of the arrangement of these unit cells. So let us now understand the unit cells and the lattices better. A regular 3-dimensional arrangement of points in space, that is known as a crystal lattice. What are the characteristics of the Bravais lattices? Each point in the unit cell, or in the lattice rather, each point in the lattice, if you see each corner of each cube actually represents an atom. Each corner, we call them the lattice points. So each point is a lattice site or a lattice point. What does the lattice point mean? That whatever is the constituent particle which is making that crystal, it could be an atom, it could be an ion, it could be a molecule, whatever is the basic structure, molecular structure or atomic structure, which on repeating will give you first the unit cell and then the lattice. That unit is one corner of the cube, and these points are known as the lattice points or the lattice sites. I'll just give you an example. You can imagine, as I told you, that a cube would be the simplest kind of unit cell. And let me imagine that I have this set of balls, okay, the table tennis balls, and I'm placing them one over the other. When I place them like this, one over the other, can you notice you're getting cubes? You see 4 here and 4 here. And if you look here, you'll see these 4 will make one cube because there are 4 behind it and 4 in front, 4 white, 4 orange. Similarly, 4 orange and 4 white are in the back. So they're making a cube. These are making cubes, if you see. And then when you expand the structure, it results in the formation of a lattice. So how does it expand? Let me start expanding it now. So let me imagine that now, since I have these 2, now I have a 3rd layer over it. There, ball over ball, and a 4th layer over it. And now it is like placing the bricks, and the 5th layer over it. Do you notice? You will be able to see the squares very clearly, the unit cells, the squares, and if you see, the squares are being repeated in all directions, resulting in that crystal lattice. So the unit cell actually is not a cube. It is only these balls, the constituent particles, and the cube is imaginary. The lines are imaginary. The lines are only drawn to give us an idea what the basic structure is, while in actuality you only have the particles, that is the constituent particles, which are present in a certain pattern, which gives you an idea what the unit cell may be. And then the unit cell expands and it gives you the entire crystal lattice. And I told you there are different kinds of lattices that are produced due to unit cells, and I'll just show you how. Do you see? Here you have cubes. Now let us imagine that this arrangement changes. Instead of the balls falling one over the other, they are falling in the grooves. Now if you see, you'll be able to notice that instead of the squares, you will see hexagons. If this is the central ball, 1, 2, 3, 4, 5, 6. It has 6 balls around it in a hexagon. If this is the central ball, it has 1, 2, 3. I mean, you could see the hexagons yourself. I'll just bring it closer. Do you see the orange ball here? You will be able to see the hexagon around it. Take this orange ball here, see the hexagon around it. Take the white ball, you'll be able to see the hexagon around it. So you'd be able to see this hexagonal arrangement. And the same if you look here, the pattern is different. All you did was just use a different unit cell and expand it in 3 dimensions to get a different kind of a lattice. So God is very creative and very artistic. So what did he do? He created a certain number of unit cells originally, and as we changed the lattice points, which ones were occupied, which ones were empty, he could choose which lattice points does he want occupied, which does he want empty, does he want to stuff something in between the lattice points, and that would give rise to a different kind of a lattice. So all crystals that are known to us can be described in terms of 14 Brebet lattices, and that is why they're known as Brebet, because he guessed all the structures that were possible with these unit cells. So now you understand, I'll be doing all of this in details. This is just an idea for you to understand what a unit cell is and how on repeating a pattern you get a lattice. So each point is a lattice site in the lattice. Now I've made only unit cells. I've not made the whole lattice. That is, as now you understand what the lattice is, the entire three-dimensional arrangement. Each point represents a particle, which may be an atom, molecule, or an ion. And the lines joining the lattice points, they only bring out the geometry. If the lines are forming a cube of the particles, if they're forming a cube, it's a cubic arrangement. If it's like a cuboid, it's a cuboidal arrangement. So the lines are only to make the geometry of the unit cell clear to us. In reality, these lines do not exist in the crystals. These lines are just imaginary lines joining the lattice sites to bring out the geometry of the unit cell. Now, if you take a unit cell, how do you describe? In order to study these unit cells, you would use the cube or cuboid, whatever it is, and you would have to describe its length, its breadth, and its height. If I have a cube and I have to describe it to you, what will I tell you? How can I describe a cube without showing it to you? It is an object which has whose length is, let us say, 2 inches, breadth is also 2 inches, and height is also 2 inches. And the angles between let's say the length, breadth and height are A, B and C. Then the angles are alpha, beta and gamma, and each of the angles is also 90 degrees. Then you can imagine what the structure would be like. So that is what is done. If you have, let us say, I take this cuboid and just like this, and let me take off the lid here. Now, can you see? Imagine this to be the structure that you are seeing, an open box. This edge, this one, is A. The horizontal length here is B, and the height here is C. So A, B, and C, and all three of them have different measurements. I'm showing this to you to explain that unit cells may not always be cubes. These 3 dimensions could be different. And then if this is A, this is B, and this is C, then the angle between A and B is known as gamma. The angle between A and B is gamma. The angle between B and C, this one, is alpha, and the angle between A and C on this side, that is beta. So you use 6 of these parameters to explain the structure of the unit cell. What are the parameters which tell you the structure of the unit cell? The edges, that is the edges of the cube or cuboid, whatever it is, the A, B and C edges, and the 3 angles, that is alpha, beta and gamma. And all 3 of these would tell you the actual structure of the basic structure of the unit cell. Now, unit cells may further be of different kinds. How are they of different kinds now? You have primitive unit cells and you have centered unit cells. A primitive unit cell is a simple cube or a cuboid or whatever it is. It is the simple basic structure, right? A primitive unit cell is one, let me show it to you from here, that it gives you all the alpha, beta, gamma, and all the particles they are present, or the constituent particles, they occupy the lattice sites, the corners. So how many constituent particles would you see here on this cuboid? You will see 1 on each corner. And how many corners do we have? We have 4 in the back and 4 in the front. So we have 8 corners in a cuboid, or a cube. So you will have 8 lattice points, all of them occupied. Such a cell is known as a primitive unit cell. A unit cell in which the particles are only present on the corner positions is known as a primitive. Primitive is the basic kind, the rudimentary, the first. So that would be a primitive unit cell. Then come a little twists there. That much was not enough. Now God wanted a little creativity, a little art. So how did he bring the art about? He said, let us have a little change, a little difference in the arrangements. So how would we have the arrangements? There are 3 types of centered unit cells. The first is the body-centered. The body, now this is the body of the cuboid. The entire box is the body. So body-centered. In the center of the body, let us now imagine I have this wall here. All the corners are occupied by the walls. And now in the center of the body, you have one ball in the middle. And the box in the middle, it is stuck here. Imagine that I could somehow hang this here and then close the box. So this unit cell, if you replicate it, if you just expand this unit cell in all directions, you will get a lattice which is due to the body-centered cubic unit cell. Right? So what is a body-centered unit cell? A body-centered unit cell is one in which all the lattice, all the corners are occupied, and there is one particle, the constituent particle, which could be an atom, it could be a molecule or an ion, whatever is the constituent particle of the crystal, is present in the center of the unit cell. In the middle of, imagine something in the middle of this room. That would be a body-centered unit cell. The other type of centered unit cells is face-centered. Now how many faces does a cube or a cuboid have? How many faces does this have? Face means surface. How many surfaces does this have? One in the front, one in the back. 2, 3, one on one side, one on the other side. 4. One here now, this one, I could have kept it like this only. So 1, 2, 3, 4, 5, 6. There are 6 faces, right? So if there are 6 faces, a face-centered unit cell would be where all the 8 corners have got the constituent particles, the atoms, and each face, the center of each face also has a particle. So in every wall, in the middle of every wall, there is one particle. Not in the center of the body. You don't have to split open the unit cell. Actually, there are no walls. But these are, again, if the lines were imaginary, the walls are also imaginary. So you have the lattice points all occupied in the corners, and if you imagine these 4 lines to be making one surface, then in the middle of that surface, you have one particle. One particle in the middle of each face. So we say it is a face-centered unit cell. Now if it is a cube, then it's a face-centered cubic. But these details we'll go into later. Let us just understand this, what centered unit cells are. It's a face-centered unit cell. And the next is the end-centered. End-centered is where only 2 ends. If I imagine that you are hanging this box with a rope, and the rope passes through this. So if it passes through this, you have the rope entering here and coming out here. So 2 ends. The opposite ends, they have constituent particles. The top and the bottom, or it could be the front and the back, or it could be this side and that side. It could form 3 types of end-centered, but actually it means end-centered means there are 2, the usual lattice points are occupied, and there are 2 faces, opposite faces, which have a constituent particle in the center of 2 opposite faces. So that makes an end-centered unit cell. So this was about the unit cells and the crystal lattice. And we'll go ahead with our study of the solid state and about these crystal lattices and unit cells in our next video. I'll be telling you about the different kinds of primitive unit cells that are possible in the next video. So if you found this helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you, and bye-bye. Hello, I'm Seema and welcome to part 4 of the chapter The Solid State. Moving on with our discussion of the unit cells and the Bravais lattices or the lattice systems. Let me now explain to you what are the basic different kinds of unit cells. There are 7 basic types of unit cells, and how the different arrangements of these unit cells, of where the particles are present on the lattice points or as the centered unit cells, what are the 14 possible Bravais lattices that are possible. So let us now start understanding these systems, or the unit cells and the systems, the lattice systems, one by one. The first type of crystal system is a cubic unit cell. The unit cell is, as you know, a cubic unit cell is one where it is like a cube, where all the lattice points, and the primitive cubic cell would have all the lattice points, that is all the corners of the cube, occupied by atoms. So each one of these corner cubes, they are the ones that are occupied. They are the ones which are atoms, and when you join the lines, the centers of each of these atoms, you find that they result in the formation of a cube. So in a cube, what do you have? The different sides, that is the length, breadth and the height, all of them, length, breadth and the height, all of them are equal. So all sides are equal, that is A is equal to B is equal to C, and all angles, that is the angle between A and B, B and C, all of these, all 3 angles, they are 90 degrees. So a cubic unit cell is one which is cubic in nature, and the primitive unit cell, it has, what are the possible variations in a cubic unit cell? You can have a primitive unit cell where all the corners are occupied. You can have a body-centered one, that is one in the middle. So if you have these corners all occupied, then if you see this in the middle, this one, what would this be? This would be a face-centered cube. If you really see, the one in the middle is a face-centered. It is in the center of a face. So a face-centered cube, and if you imagine the cube which falls between all the face centers, that one would be the body center. So that is one variation that is possible, the primitive unit cell, and the body centered, where there is one cube or one ball in the center, and the face centered, as you can see, these are all face centered, where every face, in the center of each face, you have a ball or a cube. Here it is a cube, actually the atoms, we imagine them to be spheres. And there is one variation which is not mentioned here, which you will be doing later, and which is edge-centered. And since I'm holding the Rubik's Cube, it is easy for me to explain it to you right now. Do you see on the edge, each edge, in the center of each edge also you have a cube. So such cubes are edge-centered. So they are edge-centered. And of course the end-centered are top and bottom that you already know of. So in the cubic lattices, what are the different kinds of variations that are seen? In nature, we find that the cubic lattices show the primitive variation, the body-centered variation and the face-centered. So there are 3 possible cubic lattices, the Bravais lattices. So here I've made a cubic lattice, and I told you that there are 3 possible variations here. This is a simple cubic lattice where A is equal to B is equal to C, and the angles, beta angle, gamma